Hello everyone. Today we enter the core study of the sampling theorem. Next, we will develop our learning through the following topics. First, what is the sampling theorem? Simply put, it tells us how to accurately reconstruct the original continuous time signal from a discrete sampled signal. The spectrum f of j omega of the original signal f of t is symmetrically distributed from minus omega m to omega m. This shows that f of t is a band-limited signal with a maximum angular frequency of omega m. Sampling is like taking a photo of a signal, taking one shot every t seconds. If the sampling frequency is not high enough, omega s less than or equal to 2 omega m, the photo will overlap signals from different times, making it impossible to reconstruct the original signal. Only when the sampling frequency omega s is greater than 2 omega m, that is, fs is greater than 2 fm, will the sampled spectrum not overlap, and the original signal can be accurately reconstructed. Special reminder: fs equals 2 fm is the minimum sampling frequency, called the Nyquist rate. If the sampling frequency is exactly equal to 2 fm, the sampled spectrum will just not overlap. If it is below this value, aliasing will occur, just like when taking a photo with a shaky hand and the images overlap. Next is today's thinking exercise. Given that a real signal f of t has a maximum frequency fm, find the minimum sampling frequencies required for f of 2t, f of t convolved with f of 2t, and f of t times f of 2t to avoid aliasing. First, consider the signal f of 2t. F of 2t compresses the time axis of the original signal by half, like speeding up a 1-minute recording to play in 30 seconds, making the sound sharper and expanding the frequency. The original maximum frequency is fm. After compression, the maximum frequency becomes 2 fm. Therefore, the sampling frequency fs is greater than 2 times 2 fm equals 4 fm is required to avoid aliasing. The second signal is f of t convolved with f of 2t. Here, the asterisk denotes convolution. The spectrum of a convolution is the product of the spectra of the two signals. The original signal spectrum, from minus fm to fm, multiplied by the spectrum of f of 2t, from minus 2 fm to 2 fm, resulting in a new spectrum with a maximum frequency of fm. Therefore, the sampling frequency fs is greater than 2 times fm equals 2 fm is required to avoid aliasing. The third signal is f of t multiplied by f of 2t. Here, the dot denotes multiplication. The spectrum of a multiplication is the convolution of the two spectra. The original signal spectrum, from minus fm to fm, convolved with the spectrum of f of 2t, from minus 2 fm to 2 fm, giving a maximum frequency of fm plus 2 fm equals 3 fm. However, note that multiplication produces mirror frequencies, so the actual maximum frequency is 3 fm. Therefore, the sampling frequency fs is greater than 2 times 3 fm equals 6 fm is required to avoid aliasing. Summary: f of 2t requires 4 fm, f of t convolved with f of 2t requires 2 fm, and f of t multiplied by f of 2t requires 6 fm. The above theory assumes that the signal is strictly band-limited. But in practical engineering, many signals do not meet this condition. For example, speech signals may contain high-frequency noise, and music signals may have sudden impulses, such as drum beats. What should be done in this case? As shown in the diagram, on the left is the original signal f of t spectrum, which spills over the omega m range containing high-frequency components. In the middle is a low-pass filter h of j omega, like a frequency scissors, retaining only the range from minus omega m to omega m. On the right is the filtered signal f1 of t, whose spectrum is cut off within omega m, becoming a band-limited signal. In practice, We first use such an anti-aliasing low-pass filter to process the original signal, removing high-frequency noise or interference, so the signal becomes quasi-band limited before sampling. This way, even if the original signal is not strictly band limited, it can meet the sampling theorem conditions and avoid aliasing. During sampling, aliasing errors may occur. In the first row diagram, on the left is the original signal spectrum f of j omega, and on the right is the non-alias sampled spectrum f1 of j omega, ideal case. In the second row diagram, on the left is the alias spectrum after sampling, overlapped portions. Aliasing error occurs because the sampling frequency is insufficient, causing signals from different times to overlap in the spectrum and become indistinguishable. Simply put, aliasing is spectral overlap caused by sampling in time not fast enough. Finally, we discussed two practical questions. Question 1. In theory, the sampling frequency greater than or equal to 2 FM is sufficient, but in engineering it is often set to 3 to 5 FM. What? There are three reasons. Anti-interference margin. Real signals may have high-frequency noise, e.g., electromagnetic interference. Increasing the sampling frequency allows filters to remove these noises more easily. Signal uncertainty. The actual maximum frequency FM of the signal may be slightly higher than the measured value. For example, speech may occasionally have high-frequency spikes, so leaving a margin is safer. Equipment performance. Too low a sampling rate may cause errors in subsequent processing, such as encoding or transmission. Moderately increasing the sampling rate can improve signal quality. Question 2. If the maximum frequency FM of a signal is unknown, how to determine the sampling interval T? Common methods include scanning method. Start with a relatively low sampling rate. Observe whether the reconstructed signal is distorted. If so, gradually increase the sampling rate until distortion disappears. Or, use a spectrum analyzer to directly measure the maximum frequency of the signal. Then calculate T equals 1 over 2 FM. Next, we use MATLAB simulation to visualize the sampling process. The signal is x of t equals the quantity sine of 200t over 200t squared. Its time domain and frequency domain waveforms are as shown in the figure. In the time domain, the waveform looks like a bell-shaped pulse, high in the middle and low on both sides, a typical sampling function shape. In the frequency domain, the waveform resembles a mountain peak, with its maximum at zero frequency and gradually decreasing to both sides, with a maximum frequency of about 200 Hz. Since sine of 200t has a frequency of 100 Hz, squaring it doubles the frequency. This shows that the original signal is band-limited, with a maximum frequency of about 200 Hz. Theoretically, a sampling rate greater than or equal to 400 Hz can avoid aliasing. Now observe the time domain waveform when the sampling frequency is 200 Hz. In the time domain, the original bell is reduced to discrete points, because the sampling frequency equals twice the maximum frequency of the original signal. Is 200 Hz equals 2 times 100 Hz? No. The original maximum frequency is 200 Hz. So 200 Hz is the Nyquist rate. In the frequency domain, the sampled spectrum shows periodic replication. The original spectrum is repeated every 200 Hz. Since the sampling frequency equals twice the maximum frequency, the replicated spectra do not overlap, so the original signal can theoretically be reconstructed. However, if the original signal contains high-frequency noise above 200 Hz, aliasing will occur in this case. Next, observe the time domain waveform when the sampling frequency is 400 Hz. In the time domain, the sampling points are denser, almost reproducing the bell outline of the original signal, because the sampling frequency is much higher than the maximum frequency, 200 Hz. The time interval is smaller, and the variations of the signal are captured more precisely. In the frequency domain, the sampled spectrum repeats every 400 Hz, 0 Hz, plus or minus 400 Hz, plus or minus 800 Hz. With no overlap with the original spectrum, maximum 200 Hz. For reconstruction, only the main lobe, minus 200 Hz to 200 Hz, needs to be retained. This shows that the higher the sampling frequency, the denser the sampling points, and the more accurately the signal can be reconstructed. Finally, observe the time domain waveform when the sampling frequency is 100 Hz. In the time domain, the sampling points are very sparse, and the original bell shape is severely broken, appearing as isolated spikes. Because the sampling frequency, 100 Hz, is much lower than the maximum frequency, 200 Hz. The interval is too large, and the signal changes cannot be captured. The frequency domain waveform shows that the sampled spectrum has undergone severe aliasing. The original signal spectrum, with a maximum of 200 Hz, overlaps with the replicated spectra at plus or minus 100 Hz, plus or minus 300 Hz, making it impossible to distinguish which components are the original signal frequencies and which are aliased noise. This shows that a sampling frequency that is too low will cause aliasing, making it impossible to reconstruct the original signal. The final step is signal reconstruction, recovering the original signal f of t from the sampled signal fs of t. The process is as follows. As shown in the above diagram, discrete to continuous, the sampled signal fs of t is a discrete impulse train, 1 point every t seconds. Through this sequence to impulse train module, it is converted into a continuous impulse signal. Low-pass filtering. The impulse signal passes through a low-pass filter HR of j omega, whose frequency response is t for the magnitude of capital Omega is less than capital Omega sub s over 2, to retain the main lobe, and 0 otherwise, to remove high-frequency components. Convolution operation. The final output is f of t equals fs of t convolved with hr of t, that is, the convolution of the sampled signal with the filter's impulse response. The impulse response hr of t of the filter is a sampling function, as in Formula 1. With a shape like a bell-shaped pulse, it determines the quality of the reconstructed signal. If the filter is well designed, the reconstructed signal can closely match the original signal. In this lesson, we have studied the core content of the time domain sampling theorem. Sampling condition. The signal must be band-limited, maximum frequency FM, and the sampling frequency Fs is greater than 2 FM, Nyquist rate. Otherwise, spectral overlap will cause aliasing. Effective signal transformations. Time compression f of 2t expands frequency. Convolution f of t convolved with f of 2t does not change the maximum frequency. Multiplication f of t multiplied by f of 2t produces higher frequencies through spectral convolution. Engineering practice. Real-world signals should be pre-processed with an anti-aliasing filter. In engineering, Fs is often taken as 3 to 5 FM to allow margin. Reconstruction process. Through low-pass filtering and convolution, the original signal can be reconstructed from its sampled version. That concludes all the content of this lesson. See you in the next class.